Welcome back to It's a Great Day for Gauss-Bonnet, or welcome if this is your first video. Today, we're going to revisit the definition of discrete Gaussian curvature and come up with a geometric interpretation of this definition using a result from video 2. So you might want to go back and watch video 2 if you haven't seen it. We'll then prove the Gauss-Bonnet theorem for triangulated surfaces. First, we'll consider the case where our surface does not have boundary. And then we'll use that case to prove the case where the surface does have boundary. So it's a great day for Gauss-Bonnet. Let's dig in. It's a great day for Gauss-Bonnet, video number 7. So last time we talked about how we can relate the Euler characteristic to the genus of a surface, and we could think of genus as the number of holes in our surface. A sphere is genus 0, our torus is genus 1, and so on. And then we looked at 3 papers of Bernard Chazal on decomposing polyhedra into tetrahedra. So remember, this thing was an example of a polyhedra that required many tetrahedra. And we showed, or Chazal showed, that if you have a genus G surface, then you have at least G minus 1 reflex edges. And this allowed us to simplify an expression for the number of tetrahedra needed to decompose a polyhedra. So that was last time. Feedback, as you can see, we're trying landscape mode, so we'll try to zoom in and out a little bit so that things are easier to see. I also got a suggestion that I show my face in the video up in the corner. I tried this early on, but I like to write, and looking down, it was just focused on my forehead, and I feel like it didn't add much to the experience, but maybe that's something to consider for future videos. Okay, so the agenda for this video is we're going to revisit discrete Gaussian curvature and come up with a geometric interpretation of that that'll be useful in proof for triangulated surfaces. So we're going to have 2 versions of this proof, one for surfaces without boundary, and then when we have a boundary, we'll include the discrete geodesic curvature as well. So a nice short proof of Gauss-Bonnet coming up. Okay, so let's recall discrete Gaussian curvature. We have this formula, so we do 2 pi minus the sum of the angles incident to v here. So in this example, we'd have alpha 1, alpha 2, and then alpha 3 would be this backside here. And I'm going to use degree of v in a little bit of a weird way to mean the number of faces incident to v. So if this is v, here we'd have degree 3 in this example. And we can verify that if these things sum up to 2 pi, then we get, a flat surface. And what else do we like? We like larger circles to have smaller curvature than big circles. Nope, I said that wrong. So if it's a big circle, small curvature, small circle, big curvature. And this definition gives it to us. But recall that we used the Gauss-Bonnet theorem to prove this, or to derive this formula. So we want to be a little bit careful that we have sort of a warning sign here that we don't want to use circular reasoning here. So we're going to use this in our discrete proof of the Gauss-Bonnet theorem. But remember, we used the Gauss-Bonnet theorem to come up with this, so we got to be a little bit careful. So there's still a gap. We still need to prove what is called the local version, because this is the Gauss-Bonnet theorem applied to disks. So we still need a proof here, still a gap, even after this video. So just want to acknowledge that. Okay, so we're talking about discrete Gaussian curvature, and we have this nice formula, and we can compute it relatively efficiently just by summing up those angles and 2 pi minus that sum. But we can also characterize it in another way. And we already saw this in our simple form of the Gauss-Bonnet theorem for polygons in the plane. If you recall, we saw that the sum of the exterior angles was 2 pi. That's because we're making one complete revolution as we go around. But it was also useful to look at the interior angles, and we came up with this formula. And so we're considering the complementary angle. And so this is sort of nice. You can see that we're making a complete revolution. But this formula was useful as well, as we saw in the proof of Pick's theorem. Sometimes this expression comes up. So both of these characterizations are nice, And we're just switching back and forth between the fact that, alpha I is equal to pi minus beta I. These are complementary angles. So we're going to do the same thing in our setting here. So instead of considering these alphas around our vertex, we'll consider the complementary angle, and I'll call it xi here. And so this has a nice geometric interpretation. So if we swap out, instead of saying alpha I, we'll say, well, how about pi minus xi? So still the same formula, and then do some distributing, we see this expression. And we've seen this before. In video 2, this was exactly the formula for the area of a polygon on a sphere with interior angles. I should say interior here. Xi. So that's pretty cool. So I think that's a nice interpretation. And we can think of this geometrically. So we have, what is this polygon in the sphere? Well, if we extend a normal vector from each face out to the sphere, so these are right angles, normal vectors. Well, these are going to be part of great circles, and this angle will be this xi angle we saw, xi right here. I got to be a little bit more careful. So these are our vector, let me use color here. So these are my vectors that are normal to the surface. And what the blue is, we're going to end up, we're going to end up with this polygon on the sphere. Okay. And so you can verify that, okay, if we have something flat, is the area of this polygon 0? Yes, it certainly is. And so this gives a nice geometric interpretation for discrete Gaussian curvature. So we have two ways of thinking about discrete Gaussian curvature, and it's similar to this polygon case where we just consider the complementary angles. So here's our formula we saw before. We consider the complementary angles, and we get to this characterization in terms of this area of a polygon on the sphere sort of falls out in a nice way. Okay, so let's talk about a proof here. First, we'll prove it for triangulated surfaces without boundary, and then we'll use that to prove the case where we have a boundary. So let's use our new characterization of Gaussian curvature. So we say, okay, so for each vertex, so on the left-hand side of our Gauss-Bonnet theorem, we have the sum of the Gaussian curvature at every vertex, and we're hoping to show that this is 2 pi times the Euler characteristic. So we'll use our new characterization of discrete Gaussian curvature, and we'll sum that up at every vertex. So we're doing the sum over all vertices, and so sum over all vertices of this expression, where again these xi's are the complementary angles to the angles incident to our vertex. Okay, so what do we see? We see some things right away if we distribute our sum. So this first term, well, we're going to get 2 pi for every vertex, so that's a 2 pi times our number of vertices, so that's a great start. Here, we're going to get, for each vertex, we're summing over the degree of the vertex. Well, we're going to hit each edge twice. So each edge participates in 2 vertices. So here we're going to get 2 pi times e. And so this is very promising. So again, keep in mind our goal is we want to get 2 pi times the Euler characteristic. So we need just the faces to consider. So then just to be precise, we still have our double sum here. But these two terms are looking great. And so let's just zoom in on this third term here and see what's happening. So for each vertex, we're summing these complementary angles. Well, we could switch back. So let's write this as sum v and v, sum I equals 1 to degree of v of pi minus alpha I. And we're doing this, we're summing over all vertices. So we're going to consider each angle. So we're really going, okay, for this vertex, we're going around here. And then for this vertex, we'll go around there and so on. But we can reorder things. So instead of going around each vertex in this way, we can go around each face. So we're going to reorder our sum. So we're going to get a sum of f in our faces. And we're going to have I equals 1 to 3 of pi minus alpha I. So now we're going these angles face by face instead of vertex by vertex. And these are, honest to goodness, triangles. So the sum of these alpha i's on each face are going to add up to pi. And we're going to get 3 pi, for 1 for each angle. So this will simplify to sum f element of f. And we're going to get 3 pi minus pi is, of course, 2 pi. And that tells us, well, I don't need this extra line here. We're there. So this is 2 pi. Oh, I see what I was doing. This is 2 pi times the number of faces. So to plug this in here, let's zoom out a little bit. We're going to make a swap here. So this will become, copy it. So we started with our sum v and v of our discrete Gaussian curvature is equal to 2 pi times the number of vertices minus 2 pi times the number of edges plus 2 pi times the number of faces. And that is exactly the Euler characteristic. So 2 pi times chi of m here. Oh, we ran out of a little room, but that's, let's see, where's our Bonnet macaw? There he is, for our end of proof symbol. End of proof, little one there. Okay, so we did it. So just to recap what we do, well, we sort of just followed our nose. So we used our new formulation for discrete Gaussian curvature, summed it up over all vertices. We saw the number of vertices sort of just fell out. Each edge contains 2 vertices, so we get this term. And then just rearranging our sum, instead of going cyclically around a vertex, we go cyclically around a face. We get the face term, and that's exactly what we want. So we've proved this nice version of the discrete Gauss-Bonnet theorem. Oh, what did I do? Oh, I just had a concluding line, but that's okay. So we proved it. Nice. All right, so let's consider the case with the boundary. And we're going to make 2 observations that are going to really help us, and then we'll use the previous version. So what we're going to do is we're going to glue a copy of this thing to itself along the boundary. So let me try to draw it as same as possible. So we're going to sort of attach this along the boundary to get a surface without boundary. It actually might be helpful to think about, we're going to attach this directly on top of itself. So it's easier to draw as it's sticking out the other side, but really we're just going to take a copy. And so at each point you have sort of like a alternate reality of which copy am I on. But I think it's helpful to think about this as we're going to glue 2 copies along the boundary, and they're sort of on top of each other, or in one's in a different dimension than the other, if that makes any sense. Okay, but 2 observations when we do this. And so we'll call the surface we get after gluing m squared. So, because we're sort of, I don't know, copying it in some way. It made sense earlier. So the first observation is the Euler characteristic of our new surface is twice the Euler characteristic of our old surface minus the Euler characteristic of the boundary. And how do we see this? Well, we're getting 2 copies of our surface, so that's good, but we're doing some double counting when we glue these things together. So we're going to have 2 copies of these, and we're reducing it down to 1 copy. And we saw this on our genus discussion last video, that this term is 0 because our boundary is a circle. So boundary of M or a collection of circles if there's more than one component. But the important fact is that the number of edges and vertices is the same on the boundary, so the Euler characteristic of the boundary is 0. So our first observation that we're going to use in the proof is that we have this, we know the Euler characteristic of our glued surface is twice the Euler characteristic of our original surface. The next observation we want is that if we have a vertex on the boundary, well, when we glue our surface together, this vertex is no longer going to be on the boundary. And we can say our discrete Gaussian curvature is twice the geodesic curvature of the surface on the boundary, of the original surface. So to see this, we can recall our definition of geodesic curvature here. Well, when we glue a copy of the surface onto itself, so something like this, we're going to have, instead of pi minus, we'll have 2 pi minus, and instead of just summing up these angles, we're going to sum them up twice. So we're going to get, this is a little bit misleading here. So this is, what do I want to say here? This is alpha I on the boundary of M, and this is on our interior of M, and we're going to have I is going to be twice as many. So hopefully this formula is, I just wanted to remind you of the formula, but I understand I'm using alpha I in sort of a abusive way. Okay, but this is the observation we need. All right, so we're ready for our proof. So this is what we want to prove. So by 1, we get the right-hand side will help us. We'll get 2 pi times 2 times the Euler characteristic of M. So this is using this fact here. And then on the other side, we're going to use the fact that our Gaussian curvature on our glued manifold is twice the geodesic curvature on the boundary. And so we're going to get what? We'll get the sum of V element of M kV. So if you're on M, we're counting you twice on the interior. And if you're on the boundary, well, then we'll use part 2. And this is going to be 2 times the sum of the geodesic curvature on the boundary of M. So really, it can be more precise here. Oh, nope, don't want to move the whole thing. So this part is using 2. And then dividing by 2, we see that, did I have a concluding statement? Here we go, yeah, so here is what we get. And if we divide by 2, all the 2's will cancel, and we see the Gauss-Bonnet theorem for triangulated surfaces with a boundary. So very cool, sort of simple proof. Let's put our Bonnet-Macaw in here. We proved a version of the Gauss-Bonnet theorem. So very exciting. Okay, so summary, what did we do in this video? We saw a new characterization, or by considering the complementary angle, we could rewrite the definition of discrete Gaussian curvature. It gave us a geometric interpretation as the area of a polygon on the sphere. And then we talked about a proof. And so the first proof, we sort of just follow the definition. I was calling this yeah, so this should be an m squared. I updated my notation. So yeah, so we sort of just followed our nose through the definitions. And then for the second case, we used these 2 facts for the case when we had a boundary. Next time, what are we going to do next time? I don't know. There's some suggestions, but we'll see. All right, thanks for tuning in. It's a great day for Gauss-Bonnet. See you next time.